We're going to read about electromagnetic spectrum. The room that you're sitting in is bathed in a sea of electromagnetic waves. These electromagnetic waves have a wide range of wavelengths and frequencies. For example, TV and radio stations broadcast electromagnetic waves that pass through walls and windows. These waves have wavelengths from about a mile to over 500 miles. Light waves that you see are electromagnetic waves that have wavelengths of more than 1,000,000 times shorter than waves broadcast by radio stations. Classifying electromagnetic waves. The wide range of electromagnetic waves with different frequencies and wavelengths is called the electromagnetic spectrum. Figure 7 shows the electromagnetic spectrum. Though many different types of electromagnetic waves exist, they are all produced by electric charges that are moving or vibrating. The faster the charge moves or vibrates, the higher the energy of the resulting electromagnetic wave. Electromagnetic waves carry radiant energy that increases as frequency increases. For waves that travel with the same speed, the wavelength increases as frequency decreases. So the energy carried by an electromagnetic wave decreases as the wavelength increases. So you look at this little chart down here at the bottom, and you can see right here the distance from the top of one wave to the other is very long distance. Okay, these are the radio waves, microwaves. As you move along this spectrum here, you can see that the waves are getting closer and closer and closer. These have a very short wavelength between the tips. And these are very, very high energy waves. You can see this as increasing frequency. That's what you see down here, very high frequent waves. And then the decreasing wavelength is what they're saying, meaning the wavelength is getting smaller between those. Okay, these are much high energy on this side of the spectrum. Electromagnetic waves with wavelengths longer than about 0.3 miles are called radio waves. Radio waves have the lowest frequencies of all the electromagnetic waves, and they carry the least energy. Television signals, as well as AM/FM radio signals, are types of radio waves. Unlike all electromagnetic waves, radio waves are produced by moving charged particles. One way to make a radio wave is to make electrons vibrate in a piece of metal, as shown in figure 8a. This piece of metal is called an antenna. By changing the rate at which the electrons vibrate, radio waves of different frequencies can be produced that travel outward from the antenna. Detecting radio waves. These radio waves can cause electrons in another piece of metal, such as another antenna, to vibrate, as shown in figure 8b. As the electrons in the receiving antenna vibrate, they form an alternating current. This alternating current can be used to produce a picture on a TV screen and a sound from a loudspeaker, varying the frequency of the radio waves broadcast by the transmitting antenna changes the alternating current in the receiving antenna. This produces the different pictures you see and the different sounds you hear on your TV. Microwaves. Radio waves with wavelengths between about 0.3 miles and 0.001 miles are called microwaves. They have a higher frequency and a shorter wavelength than the waves that are used in your home radio. Microwaves are used to transmit some phone calls, especially from cellular and portable phones. Figure 9 shows a microwave tower. So towers like this one are ones that send and receive microwaves. Microwave ovens use microwaves to heat food. Microwaves produced inside a microwave oven cause water molecules in your food to vibrate faster, which makes your food warmer. Look at that little figure up there. Radar. Radar, you might be familiar with echolocation, in which sound waves are reflected off of object to determine its size and location. Some bats and dolphins use echolocation to navigate and hunt. Radar, an acronym for radio detecting and ranging, uses electromagnetic waves to detect objects. In the same way, radar was first used during World War II to detect and warn of the incoming enemy aircraft. A radar station sends out radio waves that bounce off of an object such as an airplane. Electronic equipment measures the time it takes for the radio waves to travel to the plane, be reflected, and return back. Because the speed of the radio waves is known, the distance to the airplane can be calculated from the following formula. Distance equals speed times time. An example of radar being used is shown in Figure 10. Because the electromagnetic waves travel so quickly, the entire process only takes a fraction of a second. Infrared waves. You may know from experience that when you stand near a glowing coals of a barbecue or red embers of a campfire, your skin senses heat and becomes warm. Your skin may also feel warm near a hot object that is not glowing. The heat you're sensing with your skin is from electromagnetic waves. These electromagnetic waves are called infrared waves. They have wavelengths over a millionth of a meter, so we're getting really, really tiny now. Detecting infrared waves. Infrared rays are emitted by almost every object. In any material, the atoms and molecules are in constant motion. Electrons in the atoms and molecules also move and vibrate. As a result, they give off electromagnetic waves. Most of the electromagnetic waves given off by an object at room temperature are infrared waves. Infrared detectors can detect objects that are warmer or colder than their surroundings. For example, areas uncovered with vegetation, such as forests, tend to be cooler than their surroundings. Using infrared detectors on satellites, the areas covered by forests and other vegetation, as well as water, rock, soil, can be mapped. Some types of night vision devices use infrared detectors to enable objects to be seen in nearly total darkness. You can see the animals there too. Certain animals over here, you can see that caption, they use infrared. Go to visible light here. As the temperature of an object increases, the atoms and molecules in the object move faster. The electrons also vibrate faster and produce electromagnetic waves of higher frequency and shorter wavelength. If the temperature is high enough, the object might glow. Some of the electromagnetic waves that the hot object is emitting are now detectable with your eyes. Electromagnetic waves you can detect with your eyes are called visible light. Visible light has wavelengths that are very, very short, in the millionths of a meter now. What you see as different colors are electromagnetic waves of different wavelengths. Red light has the longest wavelength, which is the lowest frequency, and blue light has the shortest wavelength, or high frequency. So you can see red has a little bit less energy than a blue light. Most objects that you see do not give off visible light. They simply reflect the visible light that is emitted by a source of light. All right. So ultraviolet radiation is higher in frequency than visible light and has even shorter wavelengths. Ultraviolet radiation has higher frequencies than visible light and carries more energy. The radiant energy carried by an ultraviolet wave can be enough to damage the large fragile molecules that make up living cells. Too much ultraviolet radiation can damage or kill healthy cells. Figure 13 shows the electromagnetic waves emitted by the sun, some of which are in the ultraviolet region. Too much exposure to ultraviolet waves can cause sunburn. Exposure to these waves over a long period of time can lead to early aging of the skin and possibly skin cancer. Beneficial uses of UV radiation. So a few minutes of exposure each day to ultraviolet radiation from the sun enables your body to produce the vitamin D it needs. Most people receive that amount during normal activity. The body's natural defense against too much ultraviolet radiation is to tan. However, a tan can be a sign that overexposure to ultraviolet radiation has occurred. The last part I was just going to go down was the X-rays and gamma rays. Ultraviolet rays can penetrate the top layer of your skin. X-rays with even higher frequency than ultraviolet rays have enough energy to go right through your skin and muscle. A shield made from a dense metal, such as lead, is required to stop X-rays. Gamma rays have the highest frequency of all, and therefore carry the most energy. Gamma rays are the hardest to stop. They're produced by changes in the nuclei of atoms, when protons and neutrons bond together.